Okay, guys, good afternoon. I got a haircut today and took a lot off. There's not a lot there left, but take pride in what I have. So we are looking at our next little section on electrochemistry, which is predicting reactions as being what are called spontaneous or non-spontaneous in electrochemistry. So if you have your data table handy, you're going to need that for this part. So if you don't, please pause the video and get that handy. It's kind of like when we were using the acid-base table for Bronsted-Lowry acids and bases. We had to kind of be able to switch back and forth and interpret what the table is telling us. So this is definitely the hardest table to understand in the course. There's a lot of overlap and a lot of compounds that sort of appear more than once, and it does take a bit of practice getting good at this. So I would really encourage you to work through the problems in the homework, so that when you write your quizzes and tests, it's a bit easier to find these chemicals on the table itself. So first thing we'll notice is that the layout of the table is very similar to the acid-base table, where you have a column on the left-hand side that has an arrow pointing upwards, and a column on the right-hand side that has an arrow pointing downwards. And you can see it sort of follows the same pattern as weak acids and weak bases. So they say that the compounds on the left side of the table are sort of the arrow pointing away, talks about the strength of the oxidizing agents. And you'll see that it gets larger as you go up from the bottom to the top. And so once again, you have to go back to the definitions of oxidizing agents and reducing agents. And so if you look at all the things that are under the oxidizing agent column, you'll notice that every single one of them, you are adding electrons. So for example, the first one, fluorine gas, you're adding 2 electrons. S2O8 2 minus, you're adding 2 electrons, and then 2 electrons, and then 5 electrons. And basically everything in that column is going to have electrons added to it, which means you're going to be reducing those compounds. And that is why we call them oxidizing agents, because in order for them to be reduced, they have to give up, so they have to take 2 electrons, and that would cause the oxidation of another compound. And you might notice the title of the table is standard reduction potentials. So all the reactions are written as reductions going from left to right, and if you reduce something, that's an oxidizing agent. And of course, on the other side of the table, you have the reducing agents, and reducing agents are chemicals that cause the reduction of another chemical. And so when you are reducing agents, they will get oxidized. And so as you go from the right to the left, remember they're equilibrium reactions, you're going to be oxidizing the fluorine there. Now, it might be tricky to sort of see, maybe let's look at this one. I mentioned about looking at oxidation numbers here. Like why is that reduction if you go left to right, and why is it oxidation if you go the other way? So if we just do a quick calculation, we could say X is the charge on the sulfur. So we have 2 X's, and we're minusing 8 electrons, so minus 16, that equals -2. So you get 2X, you're going to add 16 to both sides, so you get 14. So X would be 7. So the oxidation number on each one of those sulfurs is +7. On the far right-hand side, though, you have the sulfur minus 8 for the 4 oxygens, giving you a -2 charge. And so you're going to add 8 to both sides. So here, X is 6. So you have +6. So you'll notice that you have caused the reduction of the oxidation number. It's gone from 7 on the left-hand side to 6 on the right-hand side. Okay, so that's just kind of a way to read the table. The other thing that's tricky too is the fact that chemicals appear more than once on the table, and we've actually seen that in acids and bases, so that's not super surprising. But what is a bit more confusing, and I'll just sort of find one here for this is tin 2 plus. So you can see there's tin 2 plus on the right-hand side, so that's it being oxidized or acting as a reducing agent. And then tin 2 plus on the left-hand side, it acting as an oxidizing agent, in which it will be reduced in that reaction. So that's kind of familiar to amphiprotic compounds. But what's really can be more troubling is here you got copper 2 plus, and there it is as an oxidizing agent, so it's being reduced. And here's copper 2 plus, also being acting as an oxidizing agent. So not only are they on opposite sides of the table, they can actually be on the same side of the table, and you got to know how to interpret that and what that's telling you to consider when you see those kind of reactions. So today's lesson really is looking at whether or not two chemicals mixed together will actually undergo a redox reaction. And there are a few criteria for that, a bit more complicated maybe than acids and bases. But I don't think the math is as hard as acids and bases. I think just the theory probably is a little bit harder. So if you get your head around the theory, the math actually is really easy in this chapter. In fact, it's almost non-existent compared to what you guys were doing with logs and pHs and POHs and Kas and KWs and all those crazy mathematical terms we used before. So let's give you an example, one we haven't done yet before. So once again, have your data table handy. And what we'll look at is a solution that has some ions in it. So let's take a solution, and we're going to put some piece of metal in here right now. And let's make this metal zinc, okay? And the solution is going to be copper 2 plus, okay? So we got zinc metal and copper 2 plus. And I'm going to look at kind of what might seem like the exact same reaction, but I'm going to switch it up just a little bit here in that I'm going to have a metal bar. And this metal bar is going to be copper metal. And the solution is going to have zinc ions. So notice that between the two kind of setups, A and B, that we really have, a metal in a solution, so that's the same. It's just that we've switched the chemicals. We made the metals different, like zinc from copper to copper, and then we just switched the ions, so copper to zinc ions. And the question is, are we going to get a redox reaction to occur? So basically, does a redox reaction happen? Does redox occur? Now, by the word redox, what I'm referring to is a reduction reaction and an oxidation reaction. So are we getting both types of reactions occurring? And do we actually get a redox reaction in both beakers, or maybe just in one of them, or maybe neither of them? So let's take a look at our data table here. So I'm going to just scroll up the data table and find these chemicals on here. Shrink it down a bit. And so in beaker A, we said we had copper metal. So copper metal is here. There's copper metal. And we had copper metal again. And we had zinc ions. Well, actually, sorry, in beaker A, it was the other way around. So let's do beaker A first. In beaker A, we had copper 2 plus. So we had copper 2 plus. So two of those, copper 2 pluses. And then we had zinc metal being placed in there. Let's go back to the diagram there. So there we go. So zinc metal, this is for experiment A. And we have copper. So we've got zinc and copper ions. Okay, so what I would encourage you to do, especially when you're first starting these questions, is to create a little table for yourself. I'm going to create a redox. I'll just use red here, actually. Switch to black. So I'll use reduction as one column and oxidation as another column. And what I'm going to do here is I'm going to list the species or the chemicals that I have in order as they would appear on the data table. So it might make sense when I write this out, and not listing some other kind of order here. I want to be able to see a pattern here that I can predict what's going to occur. So on the data table, I had zinc metal, which was quite far down. And notice that was on the right-hand side of the table. So that's zinc metal, that can get reduced. So that can get oxidized. Okay, and then I had the copper ions that were actually above that on the data table. And I believe this one was 0.34, and I think that was 1,4. 2 plus 1, 5 actually. And the zinc one was negative 7, 6. So just if you're having a hard time finding those on your data table, I'll try to give you the numbers. It's a bit easier to locate them if you do that. Okay, so does a redox reaction happen here? Well, the answer is you still have to consider something here. One is, do you have something that can get reduced? That means do you have something that can take electrons? And then, of course, if that thing's going to take the electrons, they have to come from somewhere. So you also have to have something that can get oxidized. So in this particular question, we have things that can get reduced, and we have things that can get oxidized. So far, it's looking pretty good. You've got a chemical that can give up electrons, which is the zinc, and you've got copper that can take the electrons and wind up getting reduced here. So does a reaction happen? So this one, yes, a reaction does happen. And so what would occur is, well, let's write out the rest of the reactions here. So it says if we start with copper, we're going to get copper solid, but that would require 2 electrons. And if it's this one, we get 1 electron being used, and then that would turn into copper 1 plus. And then the zinc, if the zinc winds up getting oxidized, it's going to turn into zinc ions and 2 electrons. So those are the scenarios that could play out here. So really, as far as oxidation goes, there really is only one reaction. That would be the zinc. So we're going to say we're going to have zinc metal. We're going to have zinc metal reacting with copper 2 plus. Those are the 2 reactants. And then the products, well, for the zinc, it has to be zinc 2 plus. Has to be zinc 2 plus. And then for the copper, now you've got these 2 copper reactions. So which one do you go for? Well, what you have to look at is this arrow here we were talking about. So this arrow says that the strength of the oxidizing agents goes from highest at the bottom to, lowest at the bottom to highest at the top. So between these 2 chemicals, this one here is higher up on the table. So that is the one that is the stronger oxidizing agent. So that's the one that's going to occur. So the reaction here, we ignore that reaction. We ignore the 0.15 volt reaction. So what would happen is the copper ions would take 2 electrons that the zinc is giving it, and that would form into copper solid. So you're almost taking one solid and changing it into an ion, and the other ion turning it into a solid. So that's kind of neat. So that's our reaction there. Okay, so let's take a look at our next scenario, make a prediction here. Okay, so we've got reduction as something get reduced, and we have oxidation, something that can get oxidized. So there, hence a redox reaction. Okay, so let's think of things that can get reduced. Well, I've got zinc ions, but they're actually quite far down the table. And I have copper metal, and we sort of saw from the blunder I made there, there's actually 2 copper metals on the table, and those are at 0.52 and 0.34. So 0.52 and 0.34. Maybe I'll use a different color for oxidation. My daughter said I should use red for reduction. So, okay, so there we go. So, so zinc ions can get reduced and copper can get oxidized. So first of all, do we have 2 different species, one in which can be reduced and one in which can be oxidized? So yes, we do. And so would a reaction occur here? So in this particular setup, a reaction does not actually occur, and I want to kind of explain why. Let's say that it did occur. Let's say that the zinc did turn into zinc metal. Okay, let's just say that happened, and let's kind of ignore the copper right now. Obviously, the copper would have to change, but just so I don't do too much on the table here, and let's look at those chemicals now. So you've got copper that can be oxidized, but if the zinc wound up getting reduced, it would make zinc, which means that now you'd have another chemical that can get oxidized. So there'd be a competition between the copper and the zinc metal. And if you go back to the top of the table here, if you look at copper copper metal is right here and right there. So there's our two copper metals. And now you're going to make zinc. But according to the data table, the further down you go, the stronger you are as a reducing agent. So the zinc actually now would be the strongest reducing agent, which means it would get oxidized before the copper does. So this reaction doesn't happen because the byproduct is actually a stronger reducing agent than the copper you started with. And we could use the same logic by saying, well, let's take a look at the two coppers. This copper here would give us 0.52 or 5.52. That's going to give us copper 1 plus and 1 electron. And then the copper metal here gives us copper 2 plus and 2 electrons. Now, whichever one did happen, it still would not make sense that it happens because the chemicals you make here, these chemicals here, they're higher up than the zinc is, which means they then would get reduced before the zinc does. So you can't make reducing and oxidizing agents that are stronger than what you've already started with. That's not going to be possible. So for this reaction, there would be none. So there'd be no reaction for B. And we're going to give you a nice memory aid to help you know this in just a second here. We'll just do one more example before I do that, though. So this beaker here, nothing's going to happen there. But what you would notice happening in beaker A is the zinc metal would actually get smaller. It would get turned into zinc ions. Oopsie, it would get turned into zinc ions. So the bar would start looking smaller over time. And then what would happen is around that bar, the copper ions would start to form a layer of copper solid. And you would see this actually be quite noticeable. The solution would have been blue to start with because of the copper ions. And over time, it would become less blue, actually. It would, in terms of the reaction, it would start to decrease the concentration. So using a spectrophotometer, you'd see a decrease in the blue intensity of the light that's in there. Okay, so let's do one more example, and I'll give you sort of your memory aid for this stuff here. So let's take a look at a beaker where we have some different ions here. And I'm going to stick 2 pieces of metal in this time, okay? And let's make one of the metals aluminum, okay? So aluminum metal. And then the other metal is going to be, it's a cool metal. Let's use lead. Ions are highly toxic, act as a neurotoxin. I was just thinking when I was in university, I worked at the Wax Museum, and there was a story about John Torrington, and he was aboard one of the ships that sailed across the Arctic Ocean, trying to find a Northwest Passage, and their ships got icebound, and they were stranded in the cold north. But they actually packed a lot of supplies. They packed a lot of food, and they had a new technology back then where they sealed the food in cans. But one of the problem was they used lead solder to solder the lids of the cans together to keep the food contained. So the food was actually fresh, relatively fresh, but the lead solder had leached into the food supply. And so the captain and the sailors that were up there consumed this food. And obviously there wasn't a lot of food, so they started to get rather hungry. And there's some speculation that they actually went mad because of the accumulation of lead in their bodies, and they started to eat each other. So there's a story of cannibalism, always a good tale. Anyway, so here we go. So we got lead and aluminum, and let's put, what kind of ions can we put in here? Some different kind of ions. Let's put some silver ions in here. Actually, these are different chemicals. I'm not using A's. Oh, I can't seem to find a nice easy one. Let's use silver. Let's use silver ions. Okay, so we're going to stick with some silver here. So put some silver ions in here. And the question is, what would happen, if anything, and specifically which chemicals would react if there is a reaction. So once again, I'm going to do my table here, my reduction oxidation table. And you should get a pretty good sense pretty quickly here that most of the metal compounds in metallic form are always on the right-hand side, because you cannot actually reduce a metal. So for example, if you had a chemical like aluminum and you were somehow to reduce it, then you would be getting something like aluminum 2 minus or something. And I've never seen metal ions have negative charges, or at least very rarely. So I would think that the metals must be lower down. So I look at my table and I see the aluminum is negative 166. And the lead is a bit higher up at negative 1.13. And the silver ions, they actually can be reduced. They're quite high up at 0.80, I think. And that is everything. Okay, so there we go. So we've got a chemical that can get reduced, and we have a chemical that can get oxidized. So it seems like we have all the ingredients needed, but we had that up here and it didn't happen. Remember, we did that second question, it didn't actually work. So would this actually work for us? So here's our little shortcut, is that the chemicals that get oxidized, or let's do reduce first. The chemicals that get reduced, they have to produce reducing agents, or chemicals that can be oxidized, that have to be weaker than the reducing agents we're trying to oxidize. That's a mouthful of words, I know, but if you rewind the video a couple times, I think I said it correctly. So the reducing agent you produce, which in this case would be silver metal, has to be a weaker reducing agent than the reducing agent you're trying to oxidize. So lead and aluminum, they are lower down on the table. So they are stronger reducing agents. They're more likely to get oxidized. So this reaction looks good so far. Now, what about the oxidation reaction, the reducing agents? Which chemical, lead or aluminum, should get oxidized? And once again, it's about going downwards on the table. So the lower down you are, the more likely you are to get oxidized. So in this case, the aluminum is the lowest thing on the table on the right-hand side. So it is the one most likely to get oxidized, which is going to give us aluminum 3 plus and 3 electrons. And the silver actually is going to require 1 electron. So 1 electron to get reduced. Now, when I write out the reaction here, I'm sort of intentionally not balancing it right now. So if you go back in your notes, you might go, hey, he never balanced that properly. And that's okay. I'm just trying to show you generally what's going on here. So which two chemicals are the reactants? Well, the reactants would be the aluminum metal, and it is reacting with the silver ions in solution. And they're producing silver metal. That's one of the byproducts, which is valuable, of course. And you're getting aluminum ions forming in the solution. So technically that's not balanced, that reaction, but I'm going to leave that for now. What else can I say about this? What would you see, I guess? Yeah, what would you see occurring here? Like what would happen to the lead metal, do you think? Well, the lead metal, it does not get reacted here. It's actually left alone. So the lead metal, the pieces of metal you see there, would stay the same size. But the aluminum metal, it actually would start to get smaller over time. And so over time, you would see this decrease in the size of that metal. And what would be happening is the aluminum from the metal would be turning into aluminum 3 plus ions, which you might remember from last chapter actually would make the solution slightly acidic because it's actually a metal ion that forms one of those hexachloral things. And the silver metal, so the silver ions, they would actually be turning into silver solid, and it would actually look like this fuzzy little layer forming around the outside of that. And I'm going to see if I can go into school and set something like this up and maybe make a little video to show you guys that, so it's sort of a bit more clear what's going on here. But that's what would occur in this reaction. So what is the memory aid? What is the memory aid to know? whether or not this is occurring. So I call this a step-down reaction. I don't think that's actually a proper or official chemistry name for this, but I just memorize it as a step-down reaction. And so what I'm going to do here is I'm going to do a little bit of circling on the diagram the chart I just did here. So we said that silver was going to get reduced and aluminum was going to get oxidized. So if you think about a staircase, if you start at silver and you kind of go downhill, then at the bottom of the stairs, you're going to find the aluminum. So that is, when you look at the data table, the silver reaction, the one that's being reduced, is higher up than the aluminum reaction. So that's going to be what I'm going to call a spontaneous reaction. And by spontaneous reaction, what I'm saying is that this reaction will occur spontaneously. That means it does not need any help to make it go. There are other reactions in this chapter that are what we call non-spontaneous, but doesn't mean they can't happen. It just means they won't happen on their own without a little bit of assistance of some sort. And we'll talk more about those kind of reactions later. So the first part of the chapter really is about spontaneous reactions and ones that occur spontaneously. There's no extra thingy-majiggies you got to add to make it happen. So let's take a look at the first reaction then. Let's go back to the first reaction. So remember we said we had copper ions. They could get reduced, and we had zinc metal, and that could get oxidized. And notice, once again, if you think about going from left to right, that is a step-down reaction. The copper is turning into the zinc. And so we refer to that as a step-down reaction. So that would be a spontaneous reaction, one that occurs without any assistance, any kind of energy being put into the system or something. So let's look at the reaction that didn't work, the one we said that would not happen actually. And we gave kind of a more detailed explanation why it didn't happen, but let's use sort of a shortcut way to figure this out. So we started with zinc ions this time and going to copper metal. So once again, I'm going to use my silly analogy of a staircase. So here you are at your zinc ions, and you're trying to get to the top of the stairs where the copper metal is. And so that is going uphill. And so we're going to say that that is not spontaneous. Doesn't mean it couldn't ever happen, but it would never ever happen on its own without some kind of assistance. And once again, that's a different type of topic than we're going to be looking at right now. So all we're looking at now are reactions that are spontaneous and ones that I would call step down. And I think the easier way to do it is on the data table. I'm just going to pick two chemicals. I'm going to erase these guys here. I'm just going to randomly choose which chemical. So I'm going to pick, let's pick, I don't know, iron 3. There's iron 3. And let's put it with nickel metal, okay? So we've got iron 3 and nickel metal. So what kind of reaction would this be? Would this be step down or would this be step up? And would it be spontaneous or would it be non-spontaneous? Well, we've got that way up on the left side and this way down on the right side. So if I was walking here, I'd be going down the staircase from one to the other. And so we say that is spontaneous. What about, let's just pick random chemicals again. Let's say you had tin 4+ and you had aluminum. Do you guys think that would be spontaneous or not? Well, that would be spontaneous because from going from zinc 4+ to aluminum, you're going downhill, and that's going to be classified as our new spontaneous reactions. So let's just try one more example, and then we'll do some specific ones here. And so once again, I'm just randomly picking things. Let's say manganese ions and iodide ions. Okay. So once again, we got something that can get reduced. We got something that can get oxidized. But do you think this would be spontaneous, or would this be one of those non-spontaneous cases? Well, we're going up the hill, upwards. So that is considered to be a non-spontaneous reaction. And once again, it doesn't mean it does not ever happen. It just means it will never happen without assistance. You need some kind of assistance to make it go. And it'll make more sense as we go through the chapter what I mean by assistance. Okay, so get rid of all these lines here. Okay, so let's do a specific example now. and see if we can use the data table and this idea of step-down reactions being spontaneous. So I just want to make sure I choose a reasonable question for you. That's going to work pretty good. Okay, so let's say, just do example here. Let's say we mix tin 2+ and cobalt. And I don't want you to tell me the products, just basically, do you think there'll be a reaction? Yes or no? So is there a reaction? So just kind of a yes or no question. I'll give you one more pair here. Let's try, yeah, that actually might be kind of tricky. Let's try. Let's try nitrate with calcium. So not cobalt, but calcium. Okay. Okay. So I think for the first one, I'm gonna guess yes. I haven't looked at the data table yet, but I'm pretty sure that's going to work. But I'm going to have to look. And the nitrates, I'm going to say no to. Okay. So let's see if we can make make sense of this, and whether or not I'm right with my prediction or not. Okay, I did base this on sort of what I remember about the table, so I'm hoping I'm kind of right with my placement of things. So I'm going to take the first one, tin 2+ and cobalt. So let's just do that, and then we'll do reduction and oxidation. So as far as cobalt goes, cobalt has to be on the right side. It's got to be a metal that gets oxidized. And tin 2+, it's interesting that tin 2+ is going to appear on both sides of the table here, actually. So I'm going to have to go take a look here. So where are we here? So cobalt is right about, just saw it, there we go, right about there. Okay, it's cobalt, so it is on the right side of the table. And tin 2+ is here and here. Okay, so we actually have it being reduced and oxidized. So we've got tin 2+ and tin 2+. So first of all, would there be a reaction? Well, yes, and because what we need here is we need something that can get reduced and something that can get oxidized, and we do have that. We've got tin 2+ that can be reduced, and we've got the cobalt that can be oxidized. In fact, the cobalt would have to be the thing that gets oxidized because it's the thing lowest down on the table. Now, what would not happen though is you can't say this. You can't say, well, look, this is higher than this. So you said the higher thing matters, but it actually is the higher thing under the oxidizing agents. And so really this is the highest oxidizing agent, the highest thing that can be reduced. And this, the one down this way, the cobalt is the most likely one to get oxidized because it is the strongest reducing agent. So the reaction should be between those two and then produce the subsequent products that they say they form. Okay, so that's step down. There's a step down reaction. Now the nitrate one is a tricky one that I haven't actually covered with you yet. So I can sort of see if you said yes to this. So once again, I know that calcium is really low down the table, and it's something that can get oxidized. And then the nitrates actually are on the table, and I think they occur twice, if I remember right. There's NO3-, and that's at +8, so near the same as silver. And then there's another one that is even higher, or sorry, +0.8. And there's one even higher up that is 9.6. Okay, so +9.6. And so you might say, well, should there be a reaction here? Well, I think so, because this is I've got something that can be reduced and I have something that can be oxidized, and it does follow this step down thing that Dixon was saying. It's got this going downhill kind of feature to it. So really it seems to be reasonable to say that this would cause a spontaneous reaction, but it doesn't occur. And the reason for that is if you look really closely at the two nitrate reactions, besides the electrons, you actually need a second reactant. So if you look at the 801, you need 2 nitrates, which you probably easily have here, but you also have to have 4 H pluses, okay? And for the other nitrate one, you need to have 4 H pluses. Okay, and nowhere in the reaction were we told that. We weren't told that this had 4 H pluses or any kind of H pluses there. And you might say, well, but hang on a second. This is nitrate, which means it's in solution, which means there's water there. And you remember from last chapter that even in neutral water, there's hydronium present, like you actually have H pluses there. So the question is, well, why wouldn't the H pluses in the water work here? Like, why wouldn't they work? And the reason for that is if you look at the very top of the table, this is pretty important here. At the very top of the table, it says ionic concentrations are all at 1 molar and at 25 degrees Celsius, which means, if you think about it, it means that these reactions that we're looking at, I'm going to put a box around the nitrate ones. These nitrate reactions here, they require that the ion concentration be 1 molar. And if you think about that, if you had 1 molar H plus, that pH would be at 0, right? So that would be an incredibly acidic solution. So you can do these reactions, like it would be spontaneous if you were working under acidic conditions. But we weren't told that. We weren't told they were acidic. So we kind of have to assume that when I say you have nitrate here, you have some nitrate, that you have to assume that it's just like a glass of water with some nitrate ions in it. So it wouldn't by default be acidic. So that reaction does not happen because there are no hydrogens present. If there were hydrogens present, then yes, definitely a reaction would happen between the calcium and the nitrates. So I hope that kind of makes sense. But in fact, that raises a whole another issue then when you're looking at the data table, because look at so many of these chemicals in the upper region here, H plus, H pluses, H pluses, H pluses. At the bottom one there, but lots of them have the idea that you need to have hydrogen ions present. And so if you just had, let's say you had just had permanganate, this ion here, if you just had that alone, there's no way that that could undergo reduction unless it was under acidic conditions, because it says you need to have 8 H pluses to make it react. So keep that in mind also when you're reading the data table, that if it says you need H pluses and you don't have any information about the solution being acidic, then you cannot just say, oh yeah, it happens. It actually won't happen. So those reactions require H pluses. So once again, you can see this data table is quite a piece of work to get your head around. So I'm just going to do a couple more little examples here, and then we'll stop there because you guys are probably getting tired. So let's say you had a list of chemicals. So which chemicals will oxidize, let's say cobalt, because we know where that is now. So the same cobalt here. So which of the following chemicals will oxidize cobalt? So I'm going to give you sodium ions. I'm going to give you chromium, I2, aluminum, and iron 3+. Okay, so once again, you're going to have a step down reaction. You're going to have a chemical that can be reduced and a chemical that can be oxidized. And you got to make sure no hydrogens are supposed to be present with those. So there's one chemical here that I'm pretty, or two chemicals here, I think I'm pretty safe on saying are not going to react with cobalt. But we can look on the table here. Cobalt's a metal, chromium's a metal, and aluminum's a metal. So all three of those are metals, which means all three can only undergo oxidation. So they should be on the same side of the data table. So I'm going to basically make an assumption that that's out. The sodium ions can be reduced, but I think they're actually quite low down on the table, which might create a step-up reaction. I2, I think, is quite high up on the table, so I'm thinking maybe, probably. And then iron, I totally forgot where that is. So let's see if we can, I'm gonna have to go back and forth here. So let's take a look for cobalt first, okay? So let's get rid of all this stuff here. So cobalt is sort of middle of the table, and so cobalt would be right there. Okay, cobalt's there, and aluminum is right there. And what was the other chemical? Aluminum and chromium. And chromium is right there. Okay, so it seems to me that this is not going to be a situation where those metals are going to react with the cobalt. So I can almost get rid of those right now. Now the I2 is quite high up. I2 is right here. Okay, I don't need any H pluses for that one. The sodium, way down here. Okay, so I'm gonna put these guys in orange. Okay, so they're not going to react with the cobalt. The sodium is actually on the left side of the table, so it should be okay, but it's actually lower than the cobalt. So I'm going to say no to sodium, no to aluminum, no to chromium. Okay, so they're not going to react. And then we also had iron 3 plus and I2. I think I marked that right. Iron 3 plus. Iron 3 plus. Oh, there we go. That's iron 2 plus. Maybe I can't see here. Yeah, make this bigger. Maybe there's no iron 3 plus on here. So I'm seeing iron 2 plus and not 2. Maybe I wrote that wrong. I think I might have wrote that wrong. So let's say iron 2 plus, okay? I shouldn't test you on things that aren't on the table, okay? So we'll get rid of that. Let's say iron 2 plus, okay? So iron 2 plus is, where are we here? Iron 2 plus is here. So it is a little bit above, oh, sorry, so it's above the other metals that don't react, but it's below the cobalt here. So this would have been step up, so that's not going to occur. This would have been step up, that's not going to occur. So really it's just the I2s that are going to react with the cobalt, okay? There's a lot of jumping around here. So no to the sodium, it's too low down, and no to the iron 2 for the same reason, not quite as low down. And then the I2, though, would react with the cobalt. Okay, so let's try last example for today. If I can create a good one here. Okay, so I'm just going to pause the video for 1 second just to get the setup for this right. So just give me 1 sec here. Okay, here we go. So we have a fictitious half cell reaction mechanism here, as you would see on the table. And that is A2 plus reacting with 2 electrons to form A, and then B2 plus, and then C2 plus, and then D2 plus. And what we're going to be told that this order in the green box is not the right order you would see it on the table. So what we're going to really be asking you to do is to reorder this. Or we might ask you something like, which is the strongest reducing agent? Okay, so which is the strongest reducing agent? So we have to remember that the oxidizing agents are things that are getting reduced, and the reducing agents are the things that are getting oxidized. So if we were correct with our data table, then D should be the strongest oxidizing agent because it's the one lowest down on that list. That's what the rule said. But if this is not the right order, then it could be A, could be B, could be C, could be D. So we're going to use the information in orange, or sorry, yellowy kind of color here, to determine what is the correct order here. And sometimes this is, I mean, I'm not sure if you like puzzles or not, but it's kind of like a little puzzle, like you're just trying to piece things together here. So I'm going to draw a little bar down, and I'm going to rewrite these cells according to this information. So it says B2 plus reacts with C, which would actually be true because C is lower down, so that would be true. But it says it does not react with D. So it does not react with D. So really, the way the table is written right now, it's partially true, but it's also wrong. So I'm going to rewrite my B2 plus. Go B2 plus 2 electrons goes to B. Now, in order for that to react with C, the C has to be lower down than the B. So I'm going to write C2 plus 2 electrons equilibrium with C. And notice how I'm leaving a little space here, because that's because I might need to add one of the reactions in between there, but we'll see. We'll see what happens, okay? So B2 plus reacts with C, so that is true. And then it says that B2 plus will not react with D. So what that means is that would have to be a step up reaction, which means the D reaction has to be above it. So B2 plus will not react with D because that's step up, but B2 plus would react with C. So far the red things are kind of making sense. The second bullet says that C will react with D2 plus. So really, according to the first bit of information, that already kind of makes sense because D2 plus is higher than C, so they should react, they should work together. So I kind of dealt with both those criteria. And hopefully this last bit of criteria will help me really narrow down where things go. So it says A2 plus reacts with C, but not with B. So A2 plus, it's getting reduced. It has to be able to oxidize C, but not react with B, which means the A2 plus reaction must fit into this little column here, this little row actually, to form A. So that is the order of things. So once again, let's just double check to see if we agree with that. So I'm going to say B2 plus, that should react with C. Yeah, it does. It does not react with D. That's true. We know that C should react with D2 plus. And according to the way I've written it, that already is, right? And finally, A2 plus reacts with C. So A2 plus would react with C, but it would not react with B. So it's between those two. So which chemical is the strongest reducing agent? Well, these are the reducing agents. So it would have to be the one lowest down on that side of the table. So the strongest reducing agent would be C. And the strongest oxidizing agent would be D2 plus. Didn't ask us that, but you might get a different question than this. Okay, so that might be a bit of a long video today, but I think it does cover a fair bit of different things here. So hope you guys are doing well, and we will talk to you soon.